Dear students, I welcome you for the today's lecture related to the closures for the vessel. Now closures, generally for fabrication of a vessel, we use a flat sheet and then give a specific curvature to that flat sheet which is available, and we give a curvature to that flat sheet so that we are making a big pipe for. But as a process fluid or process material has to be there in the vessel, it should have a certain residence time, and for that purpose we are closing this vessel from the bottom as well as from the top. So there are two heads, one is provided at the top of the vessel and another that can be provided at the bottom of a vessel. So these heads, they play a very crucial role in the fabrication and the designing of the pressure vessels, and it is one of the most important parts after the shell. So if looking at the figure, we can have or we can classify the heads as the flat plate head, then the formed heads. In the category of the formed heads, we are having the standard shallow disc head, Torispherical head, elliptical head, hemispherical head, and conical heads. So this is the basic classification for heads. That is, one classification is a flat plate. That means we are simply using the flat plate which will cover the vessel. However, formed heads, they are nothing but you are giving the specific desired shape, and that can be the standard shallow disc head, torispherical head, elliptical head, hemispherical head, or conical head. These are the different types of the heads in the category of formed heads. Now looking at this figure, you can see the different closures used for vessels. Now this is the in the first figure, the simple flat plate that is used here, the flat plate that is used to close this small size vessel. Generally this flat head, that is the most common and the most cheaply available in the market, that is simply cut from your flat sheets. Then comes the formed head. All these are the different formed heads. That is, the a certain dishing has been provided, a curvature that is provided. That is, curvature is the dishing that is provided. This is a huge head that is being fabricated by simply hammering the flat sheet. So this is the hammer press, and for which the hammer is being used to give the desired curvature. So this is like similar to your household vessels. We are having the kadhi, we are having the vessels in our household. So it's different types of the bottom which we can observe in our household purposes, and such different shapes are being provided. They are used with this specific purpose. Then this figure, that is second figure, it is having a certain different curvature that is provided, a pattern or change in the curvature that is going to give you the different names, that is your Torispherical head, elliptical head, hemispherical head, and conical head. That is the difference in the curvature that makes the different sense. So here I can have this simply flat sheet which I have shown in this first line, flat sheet. A simple dishing that has been provided in the second line. Then more dishing that is increased, that can be either your elliptical or torispherical head, and still more dishing or the more curvature that is provided to give you the hemispherical head. And then the next category, that is the conical head. The conical shape that is being provided, and generally it is at the bottommost section of the vessel. The conical heads, they are provided. So these are all the different curvatures that is being provided. If you see the first figure, that is related to a flat plate, which you can see it. This is the simple flat plate which is provided. Then to this flat plate, the certain curvature that has been provided, but the bottom section is still a flat one in this figure. टूवर्ड दिस साइड घर में की जो कटोरी होती है, उस कटोरी का शेप नीचे में फ्लैट सरफेस होता है, एंड द साइड कर्वेचर दे आर बीन प्रोवाइडेड. Then there can be a smaller curvature in this section that is also provided. First this one, then second this is. The more flat surface is there, but only at the edges the small curvature that is provided. In this case, the curvature is more as compared to this case. Now the changes in this curvature that is going to form the different types of the head. That is why we are calling it a dished head, torispherical head, elliptical head, and hemispherical heads. So as the curvature goes on increasing, these formed heads, they become labeled with their depending on their curvature. So this is the dishing that has been increased, or the curvature that has been increased. So similarly, here you can see this one is your elliptical head. This one is your hemispherical head. Sorry, this one is your hemispherical head. This is elliptical head. This is your torispherical head. The changes in the curvature makes them the different. Now, if you look at the graphical figure, this is the, for a simple flat plate, one can have the simple flat curve shape that it can be used. Then the standard shallow dished head, that is second one. Here it's a flat plate that is available, but a certain curvature that has been provided at the edges. So this is the standard shallow dished head. Then in the torispherical head, and which is the most commonly used in the industries, it is either the torispherical head or the hemispherical head. These two heads are mostly used in the our chemical industries. Now in this torispherical head, the curvature, this curvature that is increased. If you will look at here, this curvature that has been increased to give you the distributed stress variation. And there is the another curvature which is at the edge, that is called a knuckle radius, and this one is your crown radius. The next is the elliptical head, that is generally 2:1 major axis to the minor axis ratio, minor axis to the major axis ratio, which is being generally used. That is your depending on this curvature and this edges, that is the difference. Then the hemispherical head, which is perfectly a half sphere, you can say. The next is your conical head, a certain conical head, here also a certain curvature that is provided, and then that is going to give you the uniform stress distribution. So all these are the different types of the heads. Now most common, which is the flat head, and you can see the simplest structure, that is the simple flat plate is cover, and it is either integrally formed with the shell or the welded to the shell, or sometimes it is fitted with the help of the bolts or clamps also. But the stresses induced is calculated on the assumption that the edges are simply supported or fixed. That means to this edge, the edge of the vessel, this vessel which are fixed, and the calculations are calculated based on this. These are the my edges, my hands are edges, and the upper page which is considered to be as the flat plate. So this flat plate is simply supported at the edges, and depending on that, the basic formula which is considered to be as the thickness, which is equal to the C into D under root of P upon F, where C is your constant, and D is the diameter, under root of P is your pressure, and F are the stresses. And basically we are doing all this related to the thickness calculations. What should be the thickness calculation which can sustain the desired operating conditions? Generally it is used, these flat plates, they are generally used for atmospheric operations, that is which is at a room atmospheric condition. So without any operation, that means simple, which we use in our household purposes, is the simple flat plates, and all these are stored at the atmospheric pressure. There is no pressure inside that vessel. uh, then at the junction, the stress concentration is more. So this is the point of the junction, that is a vertical shape and the flat plate. At this point, the or the junction, the stresses concentration is the more, because the stresses are not uniformly distributed. Curvature hai, so stresses will be more uniformly distributed. But if it's edge, then the now you can see this, the flat vertical plate. Here the edge you can see in this figure. So, as the edge is there, less distribution of the stresses is there. Now I have increased the area in this knuckle radius, or the curvature of this section. So you can have the distributed stresses over that. In this case, the stresses are concentrated to one point. Here the stresses are distributed in this area. And this is the reason why the formed heads, they come into the picture, is the limitation of the flat heads, that the stress concentration will be there in case of your flat heads. And as the stress concentration is more, you will be requiring the more thicker material to sustain the given stresses. And that is why, to reduce the cost of the vessel, to reduce the cost of a head, we are using the formed heads which are giving the desired shape, which will reduce the stress concentration. That means the stresses will be uniformly distributed throughout the head, and that is why this formed head come into the picture. So the stress is induced at the junction of the flat plate to the shell. The stress concentration is more, and there is always the possibility of a leakage also. So whenever there is a stress concentration, more stresses are there, there is the possibility of leakage which may arise, and that point may be the point of welding, and where the corrosion will also takes place, and so it can be the a possibility of leakages also. Then if the edges of the flat plate are simply supported, then the maximum stresses at the center, which is the same formula which we have talked here, that is the thickness, which is equal to C, that is the constant, and D, that is the diameter, under root of P and F, P upon F. So I can write F, which is equal to the F here, the stresses, which is equal to the C, that is the constant 0.31 into the P into the D square upon T square. So this is nothing but the same formula. Here the 0.31 is your C constant. And you can have the maximum deflection at the center. Now what is the deflection? As this is the vessel head, flat vessel head which is there, and if it is supported at the edges, then there is possibility that this vessel will have a deflection like this. Flat नहीं है तो deflection हो गया, change in the shape. Instead of a straight, you can have a deflection in the center. So that maximum deflection which will occur at the center, and that can be calculated by using this given formula. Then when the edges are assumed to be fully fixed, here the flat plate is simply supported, and here the flat plate is fully fixed. The constant factor that is going to vary here 0.31, and in this case of the fully fixed, you are having the constant of 0.188. So our basic formula, thickness, which is nothing but equals to the C into the D under root of P upon F. This is my P and F. इसी फॉर्मूले का मॉडिफिकेशन है this one as well as this one, with substituting the value of the constants. So it is always advantageous to consider the cost of head in terms of unit weight rather than the unit area, and that is related for your cost purpose. Because when we want to purchase a material or vessel, its cost, जो भी स्टील की कॉस्ट है उस प्लस फैब्रिकेशन कॉस्ट, that will be considered the total cost, that is rupees per kg, and that is why we have talked in the previous class, that is related to the derivation of optimum proportion based on the cost. So it is the rupees per kg is the cost. So it is always advantageous to consider the cost of a head in terms of a weight rather than the unit area. So there are some advantages of selecting the equal head and the shell thickness. Less thickness, less material cost. Then fabrication becomes easier if it's a flat plate. Then the attachment to the head to shell becomes very easy. Then fitting up the nozzles become easy. Then the weight and therefore transportation and handling difficulties are reduced. So these are the basic advantages for using the flat plate. This avoids the pressing, dishing, fishing, spinning and forging. But in case of a formed head, you require the pressing, dishing, flanging, spinning, forging. All these methods are required for fabrication, for forming the heads. Then the head thickness, that is calculated basis of the circumferential stresses. When the head is subjected to the internal pressure, your circumferential stresses acts on the inner surface, while it is subjected to the external pressure, it acts on the convex surface. Now the formed heads, in this category of the formed heads, it is your standard shallow dished head, torispherical head, elliptical head, hemispherical head and the conical head. All these are given with a certain specific shape. To close the a pressure vessel and to maintain the pressure. So that to store a fluid on the uniform pressure, a vessel having the minimum surface area and the thickness per unit volume, that will give me the most economical, and which is nothing but your spherical heads. This is spherical heads. They are the maxi having the minimum surface area per unit volume, but the cost of fabrication that becomes more and more as you go on increasing the curvature. So this is the standard dished head, which is simply provided with a certain curvature at the edges that has been provided. The even in the crown section, a certain curvature has can be provided. So this is the small dished head provided to a vessel. This plate is spun to a dish form. The radius with which the dishing is done is called the crown radius. This is the crown radius and this is the knuckle radius. This is the knuckle radius and this is the measure is your crown radius. So in order to avoid the corners, knuckle radius is formed. To avoid the corners कम करने के हैं, उस purpose के लिए knuckle radius has been provided. Knuckle radius is never less than the 3 times the thickness of the diameter. Now your Torispherical heads. The Torispherical heads, which are most commonly used in our chemical industries, that is the crown radius with which the dishing is done. If you will see in this figure, the radius, the flat plate is provided with the different curvature. So this flat plate which is provided with a curvature, and also in addition to the side or to the edges, this is the point of contact for the flat plate. Now I am changing this curvature. Instead of providing this corner, so if we were considering this corner, all the stresses which will be acting will be only on this corner, but the area that has been increased when I am providing the knuckle radius. So RK is my knuckle radius, RK, and which is provided at the corner. And at the center of the dish, that is my crown radius RC. This is the crown radius RC, and which is provided with this RC. And that can be maximum up to the D diameter of the vessel, which can be up to RC knuckle radius, or RC will have the different values. This crown radius, that can be the 80% or the 90% of the diameter, vessel diameter. So it becomes 0.8 times the vessel diameter or 0.9 times the vessel diameter. And your knuckle radius RK, which can be 6 to 10% of the crown of the diameter. So 0.06 times the diameter of the vessel. That is the 6%, you can say, of the diameter, vessel diameter. So this crown radius with which the dishing is done, which is equal to the diameter of the vessel, that is RC, which is equal to the diameter. The knuckle radius, that can be 6 to 10% of the diameter of the vessel. The head is provided with a straight flange portion of 15 to 20 millimeters. That is this 15 to 20 millimeter, it is nothing but the straight flange portion. This figure you can see that this is the straight flange portion, which is nothing but called the SF. That is the straight flange portion, which is the 15 to 20 millimeter length, 15 to millimeter to the 20 millimeter length. that is provided for this SF, that is the straight flange portion. First it's a straight flange portion, then it's a knuckle radius, and then it's a crown radius which is provided. So these three sections are there in almost all heads, that is always provided. The stresses associated with this area are called as the discontinuity stresses. सो जो भी शार्प एजेस हैं वहां पे अपने को कर्वेचर प्रोवाइड करके वी आर ट्राइंग टू डिस्ट्रीब्यूट द स्ट्रेसेस. In this case, the stresses are uniformly distributed as compared to this joint of cross section, point of contact. The sharp changes in this section and the discontinuity in the shape leads to a sudden and disastrous failure that can take place. So the straight flange portion helps to reduce these possibilities, and the knuckle radius also helps. So they are used in the pressure range between 1 kgs per centimeter square to 15 kgs per centimeter square. That is the general operating pressure where these torispherical heads they can be used. Now the most important part, that is the calculation of a thickness of a torispherical head or any head. We are having the basic formula for thickness calculation, which is nothing but thickness which is equal to the PD upon 2FJ, PD upon 2F and J. Now this formula, that is there, PD upon 2FJ, which is available for calculation of the thickness. Now in this case, the diameter of the vessel, which is same as your RC, or will have the values of 80% to 100% of the vessel diameter. 80% of the vessel diameter भी हो सकते हैं, 100% of the vessel diameter हो सकती है. क्राउन रेडियस की वैल्यू RC इज योर क्राउन रेडियस डायमीटर की 80% और 100% वैल्यू हो सकती है, 90% भी हो सकती है, 95% भी हो सकती है डायमीटर की वैल्यू. And that is why this diameter has been replaced with the value of the RC. And there is a M factor which is also provided. This factor is called the stress intensity factor. M is your stress intensity factor, and this factor will have a certain value depending on the RC and the RK, crown radius and the knuckle radius. It's a ratio of crown radius to the knuckle radius, which is M, the stress intensity factor, which is M, which is equal to 1/4 into bracket 3 plus under root of RC upon RK. And you can substitute this value of RC upon RK in the given formula, and you can calculate the thickness of a vessel. So as this M is having the value more than the 1, values will have the values more than the 1. So the thickness value that will be increased depending on this factor. So vessel thickness, which is calculated by using PD upon 2FJ factor, and M factor, that is having the value of more than 1, then you will have the value of the thickness for the head that will be the more than the value of the thickness of the vessel. So these are related to your torispherical head. Now coming to the elliptical head. Elliptical head, it is also called the semi-ellipsoidal head also. Here the major axis to the minor axis ratio, which is 2.6:1, or you can use the 2:1 ratio also, that is either 2:1 or 2.2:1 or 2.6:1. Depending on these values, you can have the various types of the elliptical heads. The point of maximum stress in the head changes with this ratio. That means the major axis to the minor axis, it's going to change this knuckle radius and the crown radius values, and which is going to help to reduce the stress concentration. So the heads shallow over from the ratio of 2.4, the maximum stresses is in a tangential direction at the outside surface of the knuckle region and is in compression. So major axis to the minor axis ratio of 2:1, which is most commonly used. The head is again provided with a straight flank portion of 15 to 20 millimeter, which is same used for your Torispherical head also. This is your straight flange portion, which you can see in this figure. This is 15 to 20 millimeter is your straight flange portion. This elliptical heads that can be used above 15 kgs per centimeter square. So as the dishing increases from simple dish to the torispherical to the elliptical and finally to the hemispherical head, the stress concentration is reducing, and as a result you can increase it for the higher and higher pressure. Now again the thickness calculation, the same formula which is used here also. The thickness, which is nothing but PD upon 2FJ, the same formula which is being used, that is 2F and J. In the previous section of the Torispherical head, we have multiplied with the help of the M, that is the stress intensity factor for the elliptical head. Now in this case we are multiplying by the V. This is nothing but again the stress intensity factor. But for calculation of the stress intensity factor, we are having the different formula for elliptical head, which is 1/6 into bracket 2 plus k square, that is 2 plus k square, where k is the ratio of major axis to the minor axis ratio. This is the major axis to the minor axis ratio. Now if a simple consideration for major axis to the minor axis ratio of the 2:1, what will be the value of k? That is the 2 will be the value of the k. So k square, that will be the 4, and as a result 2 plus 4, that is 6. So we will be having the value of 1 in case of the 2:1 as your elliptical major axis to the minor axis ratio. So all these are values. We will have the value of 1 in case of your major axis to the minor axis ratio of 2:1. So this is your elliptical heads. Then coming to the hemispherical heads. These are more difficult for fabrication. Cost involvements are more. Here in this figure you can see how the vessel that is being initially given the different shapes. In this figure, the certain shape that is provided and they are arranged like this, and here also you can see the different sections of the hemispherical head, and finally at the bottommost section you are provided with a certain dish which is going to form the desired hemispherical shape. So cutting involves more, giving the desired shape, bending that involves, and again the different welded joints that increases the cost. However, but the stress distribution or the is more, the stress concentration is less and stresses are uniformly distributed. So for the same thickness we can go to a higher pressure. That is the advantage. But looking at the disadvantage of a higher cost of fabrication, these heads are minimally used. So it provides a maximum volume and requires just half the thickness of cylindrical shell of the vessel. Then this head is difficult to form, and cost of fabrication is also high. It involves more drawing work and die casting, So discontinuity stresses are minimum, and the thickness calculation is simply PD upon 4FJ in this case. Because for spherical heads, we are using the formula PD upon 4FJ. So here we are also using the formula PD upon 4FJ for hemispherical heads. Now next is the conical head. The conical heads are the commonly used at the bottom of the pressure vessels, evaporators, storage vessels, cyclone separator, hydrocyclones, and in the number of different equipments also. It facilitates the draining of the product of the material. This helps for drainage, easy drainage. Fluid will easily flow, solids will easily flow when the curvature, when the certain angle that is provided. So a junction of the cone to the cylindrical shell has to be specially considered while designing the conical head. In this second figure, you can see the certain curvature or the knuckle radius which is also provided in this section. Here in this first figure, the cone is the perfect one, while in the second figure, the cone is also provided with a certain knuckle radius, which will uniformly distribute the stresses. More stress distribution will be there in case of the knuckle providing the knuckle radius. Now the thickness calculation, same formula again, PD upon 2FG formula, but here it is multiplied by the cos alpha factor, 1 upon cos alpha factor, and alpha is the half the apex angle of the cone. Alpha is half the apex angle of a cone. So this alpha, 1 upon cos alpha, we are multiplying with this for calculation of the thickness. Then heads subjected to the external pressure, also we can have the different types there. So the material cost and the manufacturing cost that will be involved